So how was everyone's weekend? Good? Was it full of merriment and taking the derivatives the long way? Okay, cool. Does anyone have any quick questions on the homework before we get started? Alright. So I'm just going to put up one quick little announcement, and I'll keep it up for a bit. Announcements. So yeah, there's two. And then, oh yeah, office hours. There's two, and then, oh yeah. Okay. Alright, so now that it's officially 8:30, we can go ahead and get started. So, yeah, quiz 2. It's going to be Wednesday, 9 a.m. to Thursday, 9 a.m. covering lessons 4, 5, 6. And you'll, as usual, have 10 minutes to do the quiz, and so that's that. Office hours for me, it's going to be Piazza tonight from 4 to 5. And then Zoom 6 to 7 p.m. Okay. And then extra credit 2. So the thing is that there are 3 other extra credit opportunities, each worth 2 points each for the remainder of the semester, and the thing is that I'm going to be dictating what those are. So I might have extra credit 2 opportunity coming up soon, so just keep an eye out on emails for that, or I'll say something sometime this week. So watch emails. So okay. Any other questions on any of that? All right. Okay, so lesson 7, Differentiation Basics. So the thing is that, like I said last time, well, we spent a bunch of time doing derivative computations the long way. Now, starting today and for the remainder of our time working with derivatives, we're going to be using not that. Specifically, we have a bunch of differentiation shortcuts we can use. So before we look at that, let's look at the limit definition first, so we have that off the bat. So recall the derivative of f of x using limits is f prime equals the limit as h approaches 0 of f of x plus h minus f of x, all that divided by h. All right. So that's just the limit definition we discussed last Friday. So one other thing I'm going to mention is that there are other ways to express the derivative that you'll see in the homework as well. So these include, well, f prime of x, as we had before. And then we also have what's this df dx thing. So all that says is that we're taking the derivative of f, this function f, with respect to x. So differentiate f, and then the denominator says with respect to x. Okay. And then the other way is just using, if we have y equals something, then the derivative is just y prime, or dy dx. So the first basic differentiation rule we're going to discuss is, let c be a real number. Then the derivative of that constant with respect to c, well, that's just a big old 0. Now, you might think, okay, that seems super simple, but why does that hold? Well, let's go back to our limit definition to see why. So in this case, our function f of x is just c in this case, right? So what does that tell us about what f of x plus h equals? If c is just a constant. Yep, it's just c as well, right? So one way to think of this is that if c were equal to 2, that means that you're saying, okay, if for every value of x I choose, that means f of x also has to be that same constant, in this case 2 that I chose, right? So that means even if I shifted a little bit to the left or right, depending on what h is, that's also that same constant. So if that's the case, let's go ahead and plug that into our limit definition. So h approaches 0 of f of x plus h minus f of x divided by h. So then that equals limit as h approaches 0 of, well, in this case, c minus c divided by h, except, oh, wait a minute, the numerator just goes straight to 0, doesn't it? So then we have limit as h goes to 0 of, well, this just becomes 0 divided by h. So then this whole thing just becomes 0. So we just get a big old 0 here. Okay? So regarding the constant rule, that's pretty nice and easy to see why that's the case. But now we also have another rule that's going to be extremely important. So it's called the power rule. So if we move that up a bit. So let n be some real number. Then the derivative with respect to x of x to the n, well, in this case we have what? So n times x to the n minus 1. And I'm going to put this in red because this is actually important. Important. Okay. So just something to keep in mind because you will be using this extremely frequently throughout this class. So to see why, well, let's just first focus on a couple of simpler cases. So, namely, n equals 1 and 2. Okay? So if we have f of x equals x, then we have, well, f of x equals x. Then f of x plus h would just be what? So it would, so f of x equals x, so that means f of x plus h is what? So remember, all we had to do is replace x with x plus h as per last time, right? So this would be what? X plus what? Yeah, x plus h, right? So if that's the case, we say, all right, well, limit as h approaches 0 of f of x plus h minus f of x divided by h. Well, we already have f of x and f of x plus h, so we just plug that in. So let's do that. Okay, so h approaches 0. So that would be x plus h minus x divided by h. So then, if we were to simplify all this stuff right here in the difference quotient, what do we end up with? Yeah, just a big old 1, right? Because we have the x's cancel each other out on the numerator. So in that case, we would just be left with h divided by h. But this is just a big old 1, because these cancel each other out. H goes to 0 of 1. So this would just be 1, just as a constant. So then you think, okay, well that's good, but in this case, we want something that looks a bit more like this. Well, you're in luck because remember, x to the 0 is equal to 1, right? So this is the same thing as 1 times x to the 0. So that's how we can reconcile the power rule with n equals 1 here. Okay? So then we'll just do the x squared case next, and then we'll move on. So if f of x equals x squared, then f of x plus h would then equal what? Go ahead. X plus h quantity squared. Good. All right. So plug that into our difference quotient. So limit as h approaches 0 of f of x plus h minus f of x, all that divided by h. So then we get what? So limit h goes to 0 of, well, let's see, x plus h quantity squared minus x squared divided by h. So now let's see, if we were to simplify the numerator, what do we end up with? So simplifying the numerator yields what? Go ahead.
Is it 2x plus h squared?
Right. Because remember, we have x squared plus 2xh plus h squared, just from expanding out the x plus h quantity squared. But then we have to subtract that with x squared, right? So the first and last terms go away. So we're just left with 2xh plus h squared divided by h. Okay? So then, noticing that we have a factor of h on each term from the numerator, we get that this is the same thing as the limit as h approaches 0 of what? So what does this simplify to?
2x plus h.
Yep, 2x plus h. So then we can just let h go to 0 very quickly from this to see that this is just 2x. Or again, to reconcile with the power rule, 2x to the first. So that's how we get the power rule for n equals 1 and 2. So nothing too crazy with that. And you could technically do with n equals 3, 4, 5, but that's going to get too computationally heavy. So I will just say I will leave that as an exercise to the reader. So, any questions on that? All right. So, page 2. So, now that we have that taken care of, let's focus on some other derivative rules that we'll need to know. Whatever. All right. Okay, so other important derivative rules. So let me do that. So, the first one is that if c is constant, then the derivative with respect to x of c times whatever function is equal to just c times the same derivative of f of x. So what that says is that if we were to try to find the derivative of a constant times some function we do know how to differentiate, then all we need to do is just take that constant outside and just focus on the derivative of the function we know how to differentiate, essentially, is what that's saying. Okay? And the second one d over dx of f of x plus or minus g of x, depending on if we're adding or subtracting. That's equal to, well, d over dx of f of x plus or minus d over dx of g of x. So what the second one says is that the sum slash difference, or the derivative of a sum slash difference of functions is the sum slash difference of the derivative of those two same functions. So be a bit more loose with it. What this formula allows us to do is that it allows us to differentiate term by term, essentially is what it allows us to do. So let's us differentiate term by term. Okay. All right. So that's another important one to know. And then 3 others are for derivatives of more explicit formulas, or more explicit functions. Namely, we have the derivative of sine of x equals cosine of x. Derivative of cosine of x, it's almost sine, but you actually have to tack on a negative onto it. So you have negative sine of x. So make sure you keep that in mind. And then the last one is the derivative of e to the x, which is just relatively nice. It's just e to the x. It's just itself. Okay? So, any questions on any of those? Okay. So, let's go ahead and start by applying some of these. So, for the first example, we are asked to find f prime of x if f of x equals x squared plus 4 times x to the 3 halves minus 1 over the 5th root of x to the 4th. So based off of what we know so far, it seems like the only one that can help us out here is the power rule. So it seems like we could do that for these first 2 terms, but based on how this last term is written, it doesn't seem like we can use it quite yet. But we can if we rewrite this last term as what? So let me do this. So we have x squared plus 4 times x to the 3 halves, and then minus x to the what power? Almost. If we're in the denominator, that means we have to do what? Negative 4/5, right. So, right, because remember, if we have the 5th root of anything, that means it's the same thing to the power of 1/5. And then because we're under the denominator, that means we have to incorporate a negative on the power if we want to flip it to the numerator. Okay? So using this representation of f of x allows us to work with its derivative a bit more sufficiently, a bit more cleanly. So, take the derivative, so we have d over dx. So we have x squared plus 4 times x to the 3 halves minus x to the negative 4/5. So if we take a look back above, then what we notice is that even though we have 3 terms here, wait a minute, this formula here lets us say we can differentiate term by term. So what that means is we have d over dx of x squared plus d over dx of 4 times x to the 3 halves, and then minus d over dx of x to the negative 4 over 5. Okay? So that's why this formula here is so helpful because it lets us say, all right, well, instead of focusing on the derivative as just these three terms, let's just focus on the derivative of each of these three terms on its own. Is what that allows us to do. Okay? And then one more thing before we start differentiating stuff is that, well, we have this 4 times x to the 3 halves here. Now, technically we know we can use the power rule to differentiate this, but we don't know how to quite differentiate 4 times x to the 3 halves. But we can if we use this formula right here. So that's why this formula is important, because that way it lets us do this. So first term's the same, but then we can throw the 4 outside to get d over dx times x to the 3 halves minus d over dx of x to the negative 4 over 5. Okay? Alright, so now that we know that, now let's go ahead and start applying the power rule. So let's go ahead and bring that back here. So the nice thing is that, remember, n can be any real number that we want in this context. So if that's the case, then using the power rule gives us that the derivative of x squared, well, technically we already have that. That's just 2x to the 1 from our computations here. So nothing too crazy there. But then what about the other two? So we have x to the 3 halves. So using the power rule gives us that its derivative equals what?
3 halves x to the 1 half.
Right. So we have 3 halves times x to the... So I'm just going to write this as 3 halves minus 1, just so that way we
You
can...
can slide your paper up over.
Oh, sorry.
Thank
Yep. So I'm just going to write as 3 halves minus 1 for now, just so you kind of see where things are being placed in the context of power rule. And then minus, then what? And then someone else, what would the derivative of this last term be?
Negative 4/5 x to the negative 9/5.
Right, so then negative 4/5 minus 1. Okay. So we have, that gives us what? 2x plus 4 times 3 halves, which simplifies to 6. Good. And then, so it'd be 6 times x to the 3 halves minus 1, which, as you said, was just 1 half. And then plus, because 2 negatives cancel each other out. And we have 4/5 times x to the, in this case, negative 4/5 minus 1, which, as you mentioned, is just negative 9/5. Okay? All right. So that's example 1. So any questions on any of that? Okay. So we're going on to example 2. So we have to find, in this case, we have to find f prime of negative pi over 3 if f of x equals cosine of x minus 2 times sine of x plus 3. Okay? So if we want to find f prime evaluated at some point, well, it would probably help if we knew what the derivative was first. So let's go ahead and do that. So first, find f prime of x. Alright, so let's see, we have f prime of x equals the derivative, the d over dx of cosine of x minus 2 times sine of x plus 3. Okay? So in this case, we say, all right, let's go ahead and use the rules from page 2 now, along with our constant rule. So if we do the same thing that we did in example 1, in terms of how to set things up and use our new rules, what do we end up with as our derivative? Let's give someone else a chance. Go ahead.
It's negative sine of x.
Right, so that's
minus 2 cosine of x.
right. And then that'd be it, right?
Yeah.
Okay, good. So let's go ahead and see why that's the case. So as before, split everything up term by term. So we have cosine of x as the first derivative. And then minus 2 times d over dx of sine of x. And then plus d over dx of just 3. Okay? So if we apply the derivative rules that we already have, well, d over dx of cosine is just negative sine of x. And then minus 2 times, well, in this case we just have cosine of x, as that's the derivative of sine. But, well, this is just 0 because 3 is constant, so we just have 0. So ultimately we have sine of x minus 2 cosine of x is our derivative. So that's f prime of x. So now, let's go ahead and use that to figure out f prime of negative pi over 3. So, now in this case, all we have to do now is just replace x with the negative pi over 3 in our derivative function. So we have negative sine of negative pi over 3 minus 2 times cosine of negative pi divided by 3. So now in this case, it looks like we're going to have to use stuff from our unit circle here. Unit circle. So if we use those values, then, well, let's see. Sine of negative pi over 3 would be what? We harken back to our unit circle here.
Negative radical 3 over 2.
Right. Negative root 3 over 2, right? Okay. So that's sine of negative pi over 3. And then we have minus 2 times cosine of negative pi over 3, which is just what? Yep, just 1/2, right? And another way you could see this is that negative pi over 3, if you add 2 pi to negative pi over 3, then that's the same thing as focusing on 5 pi over 3, right? So since we can also use 5 pi over 3 since these angles have same sine and cosine, right? Because remember, 5 pi over 3 and negative pi over 3 are 2 pi radians apart, yeah?
Would it be negative for the 1/2?
No, because remember, for negative pi over 3 is technically in quadrant 4,
Okay.
is one way to think of it. And another way to think of it is that cosine itself is an even function, so that this is the same thing as cosine of just pi over 3. So that's one way to think of it. Okay. So simplifying everything will give us, well, again, the 2 negatives cancel each other out. And then we just have root 3 over 2 minus just 1. Okay? So that's example 2. So any questions on any of that? All right. Question?
Wait, what 2 negatives cancel out?
These two. You have a negative here and then a negative here. So that's example 2. So any other questions on example 2? So example 3 is now we have to find dy dx, and then now we have this vertical bar and then like a x equals 1 subscript. So what this means is that we have to find, so dy dx evaluated at x equals 1. Okay? So essentially that's just different notation, but essentially the same thing as finding the same process as example 2, just with different notation. So in this case, you could sort of put it all in air quotes. This is like the f prime of 1 here. So that's all that says. So now let's focus on our y function here. So here's the thing: we don't really know how to work with quotients yet. So our best bet is to just work with what we have and simplify as best as we can. So can't differentiate quotients, and I'll say yet, because there is a thing called the quotient rule that we'll see next Monday actually. So simplify y first. Okay? So to do that, well, let's see. We have y equals x to the 6th minus 9 times x to the 3 over 3.7 divided by the square root of x. Okay? So how would we go about simplifying this? So what do you think we should start by doing first?
Bring the root x up by calling it x negative 1/2.
That could work. So this is the same thing as saying, well, yeah, x to the 6th minus 9 times x to the 3.7 over x to the 1/2. So yeah, what we could do is say, all right, this is the same thing as saying x to the negative 1/2 of x to the 6th minus x times 9 to the 3.7. Let's see how this a bit. So then that's the same thing as what? So the first term would simplify to what? So if we distribute the x to the negative 1/2 into both terms, then we have the first term is x to the what's that?
1.
So remember, so what we're doing is we're doing x to the negative 1/2 times x to the 6th, right? That'd be the first term. And then similarly, the second term is 9 times x to the negative 1/2 times x to the 3.7. So because of that, the first term would just be x to the what power?
What's negative 3?
Negative 3? Remember our exponent rules. 11 halves, right. So what we can also, and that is 11 halves, but because we have a decimal here, what we're going to do first is we're just going to use this decimals for our powers here. So we have 5.5 here, and then we have minus 9 times x to the what power? We use decimals. So same rule, same idea. So we would have 3.7 minus 1/2 as our power, right? So that simplifies to 3.2. Good. Okay. Okay, so now that we have that, we can say, all right, well, dy over dx, well, that's just the same thing as trying to find our derivative. So now we need to find the derivative with respect to x of x to the 5.5 minus 9 times x to the 3.2. Okay? So, do the same thing as we've been doing. So in this case, now we use our power rule. So we should get that the derivative is what? Does that help at all? Or?
A little bit.
Okay. So I know some people have already started pulling their calculators out. So what is our derivative, first off, before we start letting x equal 1? Go ahead.
5.5x to 4.5 minus 27.2x to 2.2. All right.
Yeah, I was gonna say, I think I got something a little different for the coefficient. So remember, we have 9 times 3.2 times x to the 2.2. So if you multiply 9 times 3.2, you should end up with 5.5 times x to the 4.5 minus, in this case, you would end up with 28.8 as your coefficient. So, okay. So that's the derivative. So now all we have to do is just say, all right, if we want to figure out what this expression here is, just let x equal 1 in our derivative. So, let's see. So now we have dy over dx at x equals 1. So now all we do is just let x equals 1 in here to get 5.5 times just 1 to the 4.5 minus 28.8 times 1 to the 2.2. So the good news is that, well, 1 to the anything is just 1. So we just end up with 5.5 minus 28.8 as our somewhat more simplified form. So if we were to simplify a bit further and or plug this into a calculator, what would we end up with for our decimal version of our answer? Yep, negative 23.3. Or if you really want to express this as a fraction, what you can do is say that this is the same thing as, well, negative 233, all that divided by 10. So, because we only have one decimal here, so that allows us to write our fraction as that. You can also check that with a calculator if you would like as well. So, okay. So any questions on example 3? So now the last example I would like to take a look at is example 4. So example 4 says we have to find the equation of the tangent line to the graph of x to the negative 3 halves plus cosine of x minus 2 times e to the x evaluated at x equals 0. Okay? So if you recall, there was sort of a 3-step process we had to abide by to get the equation of the tangent line, right? So the first step, if you recall from last time, was slope. We have to find the slope of the tangent line at x equals 0. Okay? So in this case, our a value would just simply correspond to 0 in this case. So in this case, to find the slope of the tangent line, all we got to do is just find the derivative and evaluate it at 0 in this case. Now the good news is that this step 1, now that we know these derivative shortcuts, will take significantly less time than it did last time, because last time had a bunch of nasty computations for step 1. So all we have to do now is just use our differentiation shortcuts to figure out f prime of x. So now we have x to the 3 halves plus cosine of x minus 2 times e to the x. So if we differentiate all that, then what do we end up with as our derivative? Using our formulas that we already have. Let's do some of this. Go ahead.
So 3 over 2 times x to the 1/2 minus sine of x minus 2 e to the x.
Yep. Okay. So if we just abide by our, we have to use power rule, derivative of cosine, and then derivative of e to the x. That's what we will end up with as our derivative. Okay. So all we have to do now is just say, all right, if we want our slope of the tangent line at x equals 0, well, just let x equals 0 in the above derivative here. So if we do that, we end up with, well, 3 halves times 0 to the 1/2 minus sine of 0 minus 2 times e to the 0, which will very nicely simplify to what? Negative 2, right? Because, well, obviously this goes away pretty quickly. Sine of 0 is 0, so that's out. So we're ultimately left with 2 times e to the 0, which this is just 1. So we just have negative 2 as our slope. So that's it for step 1. Okay. So now step 2 is find the point where tangent line and f of x meet, i.e., in this case, find 0, f of 0. And again, we're focusing on 0 here because this would be our quote-unquote a value in the context of what we had from lesson 6 last time. Okay, so if we just straight up plug in x equals 0 into our original function here, then what function value do we get here? So we have 0 to 3 halves plus cosine of 0 minus 2 times e to the 0. So all that simplifies to what?
1 minus 2, which is just a negative 1.
Yep, so this is 0, this is cosine of 0 is 1, and then minus 2, so this is negative 1. So that means our desired point is just going to be 0, negative 1. So, now last but not least, step 3. Take our slope and the point on the tangent line and use that to get our desired equation for it. And get equation of tangent line. Okay. So in this case, remember, in this class, we're going to be using the point-slope form to expedite things by quite a bit. So point-slope form So we have, remember, the formula for that was y minus y naught was equal to m times x minus x naught, where m was our slope and x naught and y naught corresponded to the point on our line. So in this case, just plug everything in. So we have y minus, well, negative 1 will be our y coordinate, equals m, which is negative 2, times x minus our x coordinate, which is 0. So we have ultimately y plus 1 equals negative 2x, or if you subtract 1 over to the other side, negative 2x minus 1. Okay. So that's it for example 4. So any questions on any of that? Okay. Alright. Then I guess if there are no other questions, then I'll give you guys 5 minutes of extra freedom on your Monday morning. And I'll see you guys either tonight in office hours, or I'll see you on Wednesday.
Is it Zoom 6 to 7?
Yep. Thanks. You're welcome.
Have a good one.
You too. You too.